So today we're joined by Richard. Richard is a full stack engineer at Amazon, and we're going to do a mock interview. We're going to do a data structures algorithm question. So Richard, are you ready to begin?
Cool. Yeah, I'm excited.
Okay. Perfect. So let's start with the problem. So essentially, we're going to be passed two arrays here. We're going to have one array, which is going to represent a set of apartment applicants. So there's going to be n applicants, and there's going to be m apartments. So the length of this array is n, and the length of this array is m. There's going to be n applicants, and there's going to be m apartments. Those sound very similar, m and n. And so each applicant has a desired kind of apartment size. So think of this as like people walking into an apartment, and each of these indices represents a specific person. This person wants a unit 60, size 60. This index 1 person wants a size 45 apartment. This index 2 wants a size 80 apartment. And then this index 3 wants a size 60 apartment, right? And so there's n of these people. And then there's m apartments. So think of this as the resource as to which they want to get access to. And so what is the goal of every applicant? The goal of every applicant is to get an apartment within a threshold of size. And you see this K here. And so let's just take, the first applicant. They want an apartment size 60. So if we look at all of these apartments, there's an apartment size 30, apartment size 60, apartment size 75. There's this K value. So this is going to be a plus or minus value. So we have this laid out here in this table. Looking at applicant 0, the minimum they would take is minus 5 of their preference, which is 60 minus 5, which is 55. And then the maximum apartment size they would, take would be 65 plus 5. So this K is just a plus or minus value. It's a threshold they'll accept the apartment within, right? So what is the core output we want? We want to see how many of these applicants are actually going to get matched to an apartment. So we can see that applicant 0 is going to accept apartment 1. That's because they are going to have that apartment between 55 and 65. So that's an apartment they would take. Applicant 1 won't be matched to an apartment. Applicant 2 won't be matched. Applicant 3 would be matched, and so on. So you can kind of work with this table here, kind of work with this input, think of other inputs. But the goal is we want to see how many of these n applicants are going to end up with an apartment given their preferences, given this differential, and so on. So hopefully that made sense. That was a good bit of talking, but maybe you could start with questions and we can go from there.
Sounds good. Yeah, looks like an interesting problem. Right off the bat, I have a couple questions.
Right.
First and foremost is I'm just anticipating a situation of two people wanting the same apartment, and there's only one apartment. So say for the first person wants the second apartment, right?
Right. Will
that apartment be off the listing?
Off the listing? No. So that's a great question. So an apartment can have multiple people. There's no limit as to how many people can be in an apartment. From the theoretical lens, just let's imagine we could pile 10 people in an apartment. Apartments will not go off the market once they're matched.
Okay. So these apartments will be of size like 30, 60, and 75, but like everyone who wants a 60 apartment can get that apartment.
Yes, if it falls within the threshold of their desired apartments, yes, they would be able to take the 60 apartment, and the actions of other applicants does not impact later applicants.
Okay, that's a cool point to make. Let me write down some notes right here.
Sure.
Actions of other applicants do not impact current decision, other people's decisions. And another question I have was, is this like, let's say we have K equals 5, and so for example, like 55 and 65, is that inclusive? So if say we have an apartment of size 55, will they also fit that?
Yeah, that's a great question. So it's going to be inclusive of both bounds. So if we have an apartment of size 55, applicant 0 would take that. If we have an apartment of size 65, applicant 0 would also take that as well. We're inclusive of both bounds.
Okay. Are we keeping track of, what apartments that people would like?
Well, at the end of the day, we're just going to return how many people were able to find an apartment they would end up living in. That's the only kind of data we would want to output, but you're welcome to track any internal data.
Cool.
That would help you solve the problem.
Sounds good.
If you're enjoying this video, we have plenty more awesome data structure algorithm and system design explanations on interviewpen.com. You can ask us any questions you have about any kind of topics surrounding data structures and algorithms and system design. We release 2 to 4 videos a week. You can run your code. You can talk to a personalized AI teaching assistant. And yeah, the site's pretty great. Anyway, enjoy the video.
Let's think what other questions off the top of my head. Are we taking into consideration like how far off the desired apartment is from their desired value? I'm guessing not, since it's either yes, they're gonna accept this apartment, or no, they're not gonna take this apartment.
Yeah, that's a great question. So it's going to be a binary thing. If the apartment size does not fit within that range, they're just not going to take it. If it does fit within the range, they're going to take it. I guess, yeah. On a broader scope, there could be a certain like amount to say, oh, this is a better match for this person than another. But for this specific context, we probably wouldn't need that internal data. But that's a good question. We should just look at it from the binary lens. Would the applicant take this or not? And that would probably lead us to where we need to go.
Cool. Sounds good. Yeah, I think that's most of my questions right now.
Okay.
I'll let you know if I have any others. But this is a good test example you wrote, and let me just think if I come up with any other edge cases. But for the most part, this looks pretty binary. It's the yes or no. What other edge cases could there be? So I guess at the final result could be as little as 0, but as much as the total length of n, right?
Oh, what do you mean by final result?
Like, so the output, for example.
Yes, the output could be 0. There could be no of the desires. It could match up with no apartments. So let's imagine we had 100 applicants come in and there's no apartments, then, we would return 0. Or if there's one apartment, or, if none of the thresholds are hit, these kind of like fences, these goalposts we create, then yes, we could have an output of 0.
Okay. And is K the same for across all the applicants?
Good question. K is going to be the same across every single applicant.
Cool. Sounds good. And I'm just one more question. Will the input arrays be ordered? Let's say just like the apartment array will be sorted.
That's a great question. No, there's no guarantee as to either of them being sorted.
Okay, no guarantee of being sorted. So I'm just gonna swap this around here, just so I remember that while I'm doing the problem. Cool. Yeah, I'm ready to get started. Just outline my thought process of possible solutions and we can think of. Off the top of my head, let's just first look at brute forcing. Go through the entire applicant list. I'm going to write down my brute force.
Okay.
Go through entire applicant list, iterate, and then for each applicant, iterate through apartments and see if desired is within bounds. That's a pretty straightforward solution. Should be n by n, I believe, complexity. Because you're just iterating through both of them. Yeah. All the apartments for each applicant. However, this is not very scalable. If we have like a lot of applicants, this will not scale very well. Yeah. So I think we can do better. So better solution. Right now, on top of my head, I'm thinking of what if we can store the range of available apartments. So we have like 30, 75, and 60 as the available apartments. But in reality, the range would be 25 to 35, 55 to 65, and 70 to 80. Now that's what the actual range would be of all the possible applicants. They must fit within that specific.
I see what you're doing. So you're taking K, and instead of saying, okay, we're going to go through the applicants, we're going to apply the K to each of their desires, you're saying, let's go to the end result and the actual apartments, and let's apply the K to them, and then have that constraint set. That's kind of a static pre-computation we did. Yeah. And then, okay, sure, we can go through the applicants and see, would anyone fit these ranges? Yeah. I guess, okay. I was just vocalizing that.
And then once we have this, maybe do a lot of pre-computation, do pre-computation once, and then we can just iterate through the total all the applicants, and then it'll be pretty quick.
Would that be an asymptotic improvement?
If we can, I'm thinking of...
But that was a very good point you brought up. I'm also thinking about this right now as well.
So I'm thinking of if we can somehow sort the apartments, sort the range, so the range is in order, then we can do some sort of binary search maybe, and that'll be a very good point. And then that'll be n log n maybe, so it's a little faster.
That does speed us up, and that's a good point because we can't assume that either of these are sorted, as you very well kind of clarified. So I do like the path of thinking about binary search, and essentially, we are seeing a bottleneck. You pointed out that we're going to have m times n work. The bottleneck is once we have this desire, how do we fit that into what the apartments are giving us? So, I think binary search would be intriguing to look at. So yeah, I think that's a good observation.
Cool. Let me just write that down.
Yeah.
Pre-apply K to the apartments to get a sorted range, to the range, and we want to sort that, so that'll be n log m. Sort the range, and then apply binary search of applicants onto the range to see if they fit.
I like the path we're on in terms of sorting. In general, the path of pre-computing based on like, okay, we had the brute force we were thinking of, and from there. So I do like the path we're on.
Cool. Yeah, I'm just taking a look at it, seeing if we can do any better possibly. Right. I know that we do have N applicants and M departments, so yes, we gotta do some amount of work. I'm not sure if we can do linear. Some sort of.
Do you mean linear with respect to the apartments or linear with respect to the applicants?
Yeah, the applicants.
Okay.
Like, so maybe like M plus N or something like that.
Okay. Yeah.
Not sure we can do that, since we at the end of the day we still gotta search the entire apartment range to find an apartment that fits an applicant. So I'm fine with diving deeper into the better solution that I listed out. That's cool with you.
Yeah, we can start with that and go from there. Cool. And if we need to bounce back to the brute force, we can. But sure, we can proceed and see how it goes. Yeah.
Cool. One thing I personally like to do in my interviews, just what I like to do is I like to write down everything in pseudocode first before I start coding. So I try to write down as much of the coding as possible, just to get it clear in my head, get the thought process ready. I want to pre-apply K to apartments to get a range. I'm thinking how I want to store this range. Could it be like an array list of ranges? Thinking.
We could. I would want to question, do we need to be doing, would we need to pre-apply the K to the apartments? Is that necessarily, what does that give us over just not doing that pre-computation? Because what is the core bottleneck we're solving for, Yeah,
that is a good question. I think that the pre-applying K at the end of the day, it's just a plus minus computation.
Right.
So
we can do it. Yeah. I think that. Yeah. I think we can implement it. However,
I think the value it gives is when there's overlap. So say like there's a 60 and a 65 apartment. That way we can combine the range to 55 to 70. And instead of having two different ranges. So like if we have like a lot of apartments, such as like 30. 60, 61, 62,
I see what you're saying. So you're saying, okay,
64,
we could kind of do an interval merging.
Yeah.
That's actually a nice micro optimization. That's something I didn't think initially.
It's like a little bit, but
I see. It doesn't save us asymptotically, but in terms of real lapse time, it does advantage us.
Tiny bit.
You can go ahead with that. It might complicate the implementation a tiny bit. You can do it. However, overarchingly, you have laid out a good kind of framework for how to approach it, though. So I'll just leave that.
Cool. Sounds good. I think we can. We'll first start the problem and then pre-apply if needed. If we have time. I'm thinking right now we can just first sort apartment list. That'll be like n log n. Probably using a quick sort merge sort. The predefined sorts that Java provides. Sort apartment list, and then from there we can either optionally pre-apply K and merge ranges together.
Right.
And then after that we do iterate through all of the applicants.
Right. And just a side note, we're going to be sorting lists of only integers. So beyond just a comparison sorting algorithm, which is lower bounded to n log n, we'd have access to special integer sorting algorithms that could actually do better asymptotically.
That's fair.
Just a side note, it has nothing to do with.
No, it's good point out. It's a little like bucket sort, something like that, radix.
Right.
Stuff like that.
Something like that. I mean, there's plenty of
maybe n if just numbers, and then iterate through all the applicants, and then do a binary search on each applicant to see if they fall within K of an apartment. And that looks to be about all I think the problem needed. I do need to keep track of an increment result counter if it does. Do nothing if it does not. I think that will be pretty much a pseudocode of what I plan on implementing.
Okay. I think we can go into the implementation. I think we have a good outline. Your approach has been good. And yeah, I think we can go into coding.
Cool. Sounds good. So I'll be using the total matches. I guess this is the predefined like boilerplate code we have here. So then I want to first off get an int matches equals 0. Start off with base counter and return matches at the very end. Just get that out of the way. I want to sort, going through my pseudocode. I want to sort the department first. I do apartments equals integer sort. Array.sort. Will that sort? I'm not sure.
Right.
I think this might.
And I think does that return the sorted array, or does it sort it in place? Or does it mutate what was passed in? I'm not sure. I personally I don't know, because it differs between language sometimes.
Yeah.
Sometimes they return the sorted array. Sometimes it's actually a function that mutates the input and so on. Anyway, something we can figure out later, or whatever. Yeah.
Just taking a look at online Geeks for Geeks right now.
Free promotion.
Yeah, free promotion.
It's
an online again. So I can just do arrays.sort. I don't even need the departments. So I'm assuming we can modify the apartments.
Yes, you can mutate. There's no kind of limits on function purity. That would more be a style / like context detail.
Sounds good. And this is, I feel it's arrays.sort and it's not array.sort.
Yeah.
So this will sort the array of apartments, and now so that'll be increment. Now the apartments will be incremented. So now we just sort through but iterate through the entire desired list.
Right.
So for int I equals 0, I is less than desired dot length I plus plus. See what happens now. We iterate through, and now I want to copy some of my comments here. So binary search on each applicant. I'm wondering if I can do the binary search within the same method, or if I should create a helper method. Just do a recursive binary search.
Right.
Let's see, it could be a move.
Right. It could be a move.
Yeah,
I think it would be clean to have it in an auxiliary helper. You don't have to. Obviously, logically equivalent to doing it in the same function, but if it's iterative. So you also could do it recursively. Either works. So it's your choice.
Yeah, I'm just do recursively. Private static int. Should it be int? Let's see. It's a binary search. I just want to turn a Boolean, I guess, if it fits or not.
Right. Yeah. Whether we find it in the apartments array.
Yeah.
Did we find it? And yeah, we could return the index of what was found. Either would make sense.
Binary search. So we have int start, int end. I forgot what other stuff we need for the binary search. I'm sure I'll find out later on once I actually
it's fine if you can come back and fill it, or
And now,
I don't think I've ever implemented binary search from scratch ever. Libraries always do underneath or whatever,
Yeah,
whatever.
It's been a minute.
So
Forgot if there's a Java library to help you do this, but this is usually what I've been practicing when I practice. It's always good to know for interviews
and we can leave this stubbed, or you can do binary search now, or you can. So that's set up, and anyway.
Okay. If binary search, so I need to start and end to start out with. So I'll be doing apartments 0 and apartments end. Apartments of 0 and apartments of apartments dot length. It's 1. So that would give me the smallest. This is pre-sorted, right? From line 55. That would give me the smallest apartment. So in the case of, we have 30, 75, 60. That would give me 30 and 75. Those will be sorted. So if binary search that, and then I guess we gotta the item to search for.
We also could just pass the array into the binary search. If we're doing it iteratively, we could just set the bounds, like the start and the end, within the function, and then iteratively update the start and end. Well, the way you have it set up is like, okay, we're gonna have a start and end kind of index that we recursively narrow in. We could just pass all of the apartments in, and then pass in the target, and then set our left and right within the binary search function if it's iterative.
Yeah, That's
like this is
fair.
what you were on the path anyway.
Yeah,
But
yeah.
I'm just like kind of
Yeah,
ushering us forward into what those parameters look like. So okay, yeah.
start. So
And
this
then,
be
as you were saying, the actual
start
thing we're
index.
looking for.
End index. Let's see, apartments, and then change this to 0, and then apartments.length -1, and then this will be desired of I. That'll be the one we're looking at currently, and then we just increment matches plus. That looks
Okay.
pretty simple.
Right.
Honestly, a little too simple, but we'll get into it once we into the binary search. Realize we gotta take into consideration k. So I probably send a pass on a k as well. We can optimize and get rid of some of these parameters if we see later.
Right.
But just right now, we're just gonna pass in k. So the base case is if we are on the money.
And I imagine you're doing this recursively, as you said?
Yeah.
Or-
yeah,
Okay,
yeah.
recursive. Sounds good.
Do I need a current pointer? I feel like I would need a current pointer so I would
Well,
binary search. I'll split it in half.
yeah.
Uh,
You would find the midpoint.
midpoint. So start
Right.
plus n divided by 2.
Yeah. So I would imagine the only things you need between state transitions is what is the left bound, what's the right bound, and then you compute the midpoint, and then whatever's at the midpoint, you'll say, okay, do I need to go which direction, and so on.
Yeah.
And so, right. And when we compute the midpoint, let's imagine that we could overflow somehow. Like, how would we adjust the midpoint calculation? This is like literally a detail that doesn't matter, but like,
Yeah.
Yeah.
Yeah, that's fair. So we just start from 0 to midpoint -1, and then midpoint to.
we can just do start index plus end index. That's fine too. Divided by 2. That works as well.
Yeah. I'm not sure if I think I might need -1 at the end or something like that. It's
Right.
been a while since I implemented it.
We
but-
can start with this and then
Okay.
debug it, or
Yeah, and now so it's at if start, the base case will be if start is equal to end. That means we've narrowed down on something, right?
right.
If if the start index is greater than end index, greater or equal to end index, that means we've narrowed down on something, and then we can then we narrow down on the closest match, and so now we'll see if that is within k plus or minus k. So if return apartments of start index maybe -5 is less than equal to 0, and apartments start index +5 is greater than equal to 0. So this will be like our go posts. See if we're right on the money. And I'll just be like a final true or false at the very end. So then midpoint, and then now this part we just bisect. At this point, if we still have more to search through, so then we return binary search apartments start index, and then
so we need to bake in a decision, right, to see whether we go left or right. So we would immediately return.
that's fair. Yeah.
We would need to say, okay, we have this number at the midpoint. We expect to see, for example, let's say the preferences took us a certain way. We would need to go left or right. So what would that look like?
That is, yeah, good call. Good point. Good point. Yeah. So right now, I was originally trying to do add another binary search here, but then that's just going down both paths and defeating the whole point for binary search.
Yeah, I see. I saw the way you're going. Yeah.
Yeah.
Just wanted
So if go is greater than equal to apartments of midpoint, then we would go right. Right. Midpoint end index, and then go okay. Else we will return go left, and
we could even do something where we maybe short circuit, where the way this recursion is set up is that it's going to go all the way down to the base case.
Yeah.
Within these if else's conditions, we might actually find a value that is within the threshold of the goal, where we could immediately short circuit out of the binary search. But whatever, that doesn't asymptotically help us. That helps us in real elapsed time. But yeah, this is set up for a log n runtime. And yeah, so anyway, continue. Or logarithmic.
Yeah. So I'm thinking of what else I may be missing. I realize I -5 here. I should replace with my +5 plus k minus k. I think that might be it. We'll narrow down any issues when we run it.
Yeah, whenever you're ready, we can run it and debug things. That's totally fine. Cool. To debug the.
Let's run it then. Hopefully it works. Little confetti there. I figure out.
Okay.
Arrays. Do I need import arrays?
I think we need it. Yeah, I think it's util dot. Just let's wildcard util. Import java.util dot star. Okay, I forgot to do that setup.
Sounds good. Thank you. And now.
I think arrays is under util.
Yeah. Oh, and now we are hitting.
Okay, so all right, we have an overflow going on.
Yeah, overflow going on.
So why is that happening?
It's not breaking out of the binary search, which should happen within line 76. Start index is greater than or equal to end index. So I'm assuming at one point, this midpoint calculation, it's always going to be. We'll say like if, for example, we start off with 0 and 2, right, for the apartments of size 3. Passing 0 and 2, midpoint will be 1. Then will be 1 and 2.
Yeah, so we have this overflow issue. Where could it be? We know that, okay, why is the recursion going on forever? The first place I would look is the state transitions, and it looks like you're setting the bounds. Okay, the left bound becomes the midpoint, end index.
Yeah. So what I would do to debug it first of all is take our input, 3675. Right. We have 30, 60, 75. In this case, our goal is just say if we were going down the left path, it will be start equals 0, end equals 1. If you're on the right path, it'll be start equals 1, end equals 2. Because midpoint is 0 plus 2 divided by 1.
Right.
Divided by 2. Sorry. And now within this, I'm guessing it's some 1 plus 2 divided by 2. That's 1.5 and it rounds down.
Right.
I'm thinking. So I think this is where the +1 may need to be. I remember there might be a +1 here, or it might be a -1 at the previous point.
I see. And it's getting stuck in some sort of like in between. Yeah.
Well, either the start or the end point, or both of them are not changing.
Right.
Repeat after repeat. So I believe this will fix it. We'll give it a shot.
Yeah, we'll always try more stuff if it doesn't.
It doesn't fix it. Maybe this is my favorite type of debugging, is just trying to see if it works.
Right.
But we'll go into a little bit more.
Okay, it looks like we have a different error. Okay, no, it's the same error.
Same error.
Okay.
So at this point, I would want to add some print statements and figure out which case is it debugging on, which applicant is it breaking out on.
Okay, so let's do that.
So we do system.out.println line.
So the inputs to the recursion look fine. We start out with the whole array, index 0. We pass in the desired I, which is the target. We have k.
So I'm trying to quick print some to see who I'm searching for. And that one breaks because it's a semicolon. So we'll see which specific applicant is going through, and then we'll just go step-by-step debug. Should be pretty quick.
So it stops at the first one, it looks like.
So 60. So at this case...
So it must be something fundamental to the actual function rather than like a specific input like being pathological.
Yeah.
Or maybe it might be pathological on the first one, but...
So start index is 60. Midpoint, so goal is at this point...
I mean, we're basically there. Like the overarching approach you have down. And in terms of time complexity, I think we're doing very well. I wouldn't imagine we could do better. Maybe we could, but now we're just down to, okay, let's debug this. Why is there's probably an off by a 1 error somewhere.
Yeah. That's the hard part of these problems, is find where you're off by 1. Just playing around a bit.
It would also be much easier to do this in a non-interview context as well when you're not like under pressure.
Yeah, just like figuring out where. it's wrong, but it was stuck on applicant 60.
Right.
It fails on 60, so
Right.
at this point it would go down. If go is greater than or equal to 60, so 60 is greater than or equal to apartment's midpoint. I'm actually thinking, I don't think this would actually work.
Why? Why would that be the case?
Say like if we don't do the pre-application of the range, I think there could be some edge cases where it will choose to go right, but the actual answer is within K of the last element on the left.
Right.
You see?
So when we're making that decision to go left or right, what are we looking at? What is the key data point we're looking at? So right now we would have an apartment size within our hands.
Yeah.
What are we comparing that against?
We're comparing against plus or minus K to the applicant's desire.
Right.
But I think right now when we're doing decision making to go left and right, we're not taking into consideration the K. But that provides a lot of useful value, the K, because that's a big range of possible paths to go down.
So when we enter into this function, this is kind of setting our mindset into coming into this binary search. What are we actually looking for? I think that's where we should direct our kind of mind, because right now we've passed in the goal in K, and we need to think like, what are we looking for? We're looking for a quantity between two numbers, right? And either we hit that number, we're in that range, or we fall to the left of that range, or we fall to the right of that range. So I guess that could kind of tee you off into thinking how to tweak the search to actually work.
Yeah. So right now I'm thinking of line 85. That needs to go. Something needs about this needs to change.
What are we actually looking for, right?
Yeah, if it's within plus or minus the range, not if it's greater than or equal to apartment's midpoint. Let's see. Apartment's midpoint minus K, I'm thinking. I feel like this much might break some things. We're modifying the inherent properties of binary search and how it works, by allowing some more gap room. So we're gonna get more plus one minus one.
Right. What we could say is, yeah, I see. Or I need to think about this myself. Just thinking about how we tweak the search.
Yeah, I think the easier way to do it is just to establish your ranges beforehand.
That would be fine as well. Because we're coming into the search knowing the range we want. Yeah. Like we're coming into the search, if this is 60 and K is 5, give me a number between 55 and 65. If I see a 50, then I know I need to move closer to that range, to the right. So we could adjust the search that way, yeah.
I think we still need to fit a plus one minus one issue that we have, but
right.
That's...
So I think we could rewrite the search to come into the search with the bounds. So let's actually come back to the top. Let's come back to this binary search, and we can still pass the apartments, but I think we should pass in. I don't think we need to set the we don't need to do the. Okay, so we're doing it recursively.
We could pass in the shortened subsection of the array, a subsection subarray, instead of the.
Yeah, no, pass in the index. The index is fine. Let's pass in the min and the max into the recur. Actually, no, I don't want to say how to do this because any of these ways would work. Just like, how would you do it? Yeah. And essentially at the if statement point, we would say, if the value at the midpoint falls outside of the range, it can fall outside of the range in two places. To the left, then we would want to go right. Or it can fall outside to the right, then take me left in the apartments array.
And if it's inside?
If it's inside, done.
Don't need to make decisions.
We're done.
Yeah.
Yeah, that is the bifurcation.
So I think then wouldn't that be at the binary search level, around like line 80, 85, instead of
right.
up there. So if it's
you could set them
midpoint just to make it a little more legible.
Sure.
Now if go minus K is,
or we could say if the apartment is less than the goal minus K. Meaning it falls to the left of the lower bound. That means we need to go right.
Hold on, give me a second. I'm lost.
No. I'm double thinking. I'm thinking about it right now as well. Like I haven't even reviewed the solution code. I think that is what we would want to do, right? Because if we fall to the left of the range, there's no other choice we have but to look for bigger numbers to get into the range.
Yeah.
So this is how the binary search should work.
So
there's no other way it could work.
So what are our goalposts right now? Our goalpost is
between min and max. Goal plus k, goal minus k.
But like the so we have like if it's less than that, we do binary search on left. If it's right,
We look to the right.
yeah. But then what's in between is
If it's in between, we're done. We return true.
in between of what? So what are the
In between min and max.
of
Goal minus k, goal plus k. If it's between those, we return true.
Joe minus 10, Joe plus 10.
Goal plus- yeah.
If the midpoint is between Joe minus,
If the midpoint value is between those, return true. If it's to the left of those, we need to go right. If it's to the right of those, we need to go left. We're basically there. We're literally just knitting on details right now. So let's say if midpoint apartment, yeah, okay,
equal to so this will be our within our goalposts, we return true.
yeah.
And then else if
I think we should probably invert it to say midpoint apartment is greater than or equal to.
yeah.
I think we should phrase it that way. Although this is logically equivalent, it just doesn't read as well.
Okay. Let's start from scratch. So if
So if the midpoint apartment is greater than or equal to goal minus k, greater than or equal to goal minus k.
left goalpost.
So that's our left.
And then midpoint apartment less than or equal to Joe plus k.
Goal plus k.
that'll
Perfect.
be-
Now we're inbounds. We're done.
Yeah, we're done here. This is our middle best case scenario. We
Yeah, this is
hit
best
one on
case.
the money.
Yeah.
Um,
Now let's imagine the value falls out to the left.
yeah. It's, so in that case, midpoint apartment will be less than Joe minus k.
Which way?
Does it matter which way we're searching?
Is that true? Because let's
It won't
imagine
matter.
the apartment is too small. Do we want to go up in apartment sizes, right?
Yeah, that we would just still
Right.
we would just still straight left. So if Joe is greater than apartment's midpoint, then we just
Or we would want to
We want a bigger
say,
apartment.
let's chain an else if here. So let's do an else
yeah,
if,
that's fair.
and then let's say if midpoint apartment is less than goal minus k, and then we drive the search to the right.
If
Let's say midpoint apartment,
so we flip this around.
midpoint apartment is less than goal minus k.
At this point, it doesn't be Joe minus k, just to be less than Joe, because we know. Do we know? Actually, yeah. So this will identify the clear goalposts and then make
Okay.
sure we're not overlapping. So then, if it goes,
I see what you meant, though. I see what you meant.
Yeah, if it goes to the third else condition, then we know that midpoint apartment is greater than equal to Joe minus k. However, it's filling on this clause. So then we know it's pretty much just midpoint greater than Joe plus k. And then, yeah, I think that's it. I think it's midpoint plus 1.
I see. So we don't recurse on. I see.
Might be wrong, but I hope this will do.
No, I think you're right. Sounds right to me.
3. Oh.
Okay, so why was it 3?
why are we getting 3? We'll find out which ones.
Now I'm wondering why it's 3. Maybe it was exclusive. Let me see. Oh, it should be 3. Yeah.
Should be 3.
No, because the problem statement I gave you was exclusive.
Oh. 80. Yeah,
So
yeah.
your solution is correct.
Cool.
That's a mistake on the initial part. I'll make sure to make a note of that.
Yeah, no worries.
But essentially, yeah, your code works. So let's imagine we did do it exclusive. The only thing we would need to tweak is these bounds here in this if statement and so on. So yeah, I think we're good. I think you've sufficiently solved the question, and you stepped through all of the brute force iterative stuff. Now let's kind of think about runtime. Let's think about the best we can do. I think we did already kind of mostly discuss this, but what are the time and space be and so on.
Cool. So let's look at some time, space, complexity. We already briefly talked about it, like you mentioned. But let's just delve through the entire application, the entire code. So over here, we are first sorting the apartments list. Arrays.sort uses the n log n. We could make more efficient, but make it n. However, this probably won't make that much difference, especially since end result should be n log n. So off the top, this is n log n, but could be faster with optimized sorting, such as radix or bucket. I believe those two ones. That'll be O of n. for integers. And then this will be going through an entire desired length, which will be O of n. This will be actually m log m. And then this will be of O of n. And then each binary search will be
logarithmic with respect to the apartment m. So it's like log m times n log m, something like that. And that is a better improvement over n times n.
Yeah.
As we saw before. So yeah, all this makes sense. Time and space, and then we have the recursive binary search. I imagine the depth is logarithmic on that. Space wise, any other space we're using?
Space.
I think that should be it for space.
Yeah, we're just passing in the apartment. We could. This is a tiny bit of efficiency if we keep the apartment static as a static variable,
right?
Instead of passing in every time. But that's just like my need.
Right. Okay, so I think we're good. I think we've gone through the problem. We've gone through the time and space analysis. So now let's kind of go into, again, the kind of meta analysis. Like, how do you think you did? What would you kind of improved about how you went about stuff? I think you did a really good job about clarifying your assumptions and stepping through the problem, kind of methodically, crafting an approach, and then kind of implementing it. What are your kind of thoughts on how you did and how you could do better and so on?
Cool. Yeah.
And you can bring in any experience from your interviews and so on.
Yeah. I think at the start was not bad. They honed in on a possible solution. I was pretty fortunate enough to like recognize that, hey, maybe if we sort this, we can get some sort of like binary search going on here. And I feel like n log n, that time plus is like kind of ignored. It's like the
right.
It's like the
I always feel that way too. I always say that.
We love n squared.
I try to speak up for it.
But like n log n is like
n log n gets no love, especially because it deals with nonlinear structures. Especially like you have like a binary heap, you have trees. Like anytime logarithm gets involved, or like it's just weird. You know, people don't. Or in general, you don't think about it.
Yeah.
But anyway. So yeah, I think any other thoughts or how this is compared to other interviews or?
Yeah, I think definitely could have. Binary search was debugging. That's at the end of the day.
Right.
You probably experienced this in interviews. I've experienced the same thing in interviews where like it's always some plus one, minus one.
And that can eat up the meat of like actually having. Yeah.
However, I think it is valuable for the interviewer to like see how you debug. So it's good to like walk through your debugging step.
Right. And I think you methodically did it well. You know, you started out with the start. You were like, okay, which actual apartment is the one holding us up? And then we're like, okay, let's relook at how we're doing the search and so on.
Yeah. But yeah, just working through the problem. Great interviewer. Thank you for the tips and stuff. But yeah, at the end of the day, it's just walking through, even just paper code and just like write down like what each variable should be at every step of the process and just trying to figure out what's wrong.
How does this compare to kind of your experience interviewing at Amazon or like other companies? Was this like a harder question than you normally get, or like what is the difficulty scale?
I think it's okay. I think there could be a lot of, you could see some harder ones, but this one's pretty tough, especially if you're not too familiar with binary search. But
right,
yeah, it's really depends on what.
Very rarely
if you're lucky or not.
Yeah, like you rarely ever implement binary search. So if it's been a while, it's like like it's a fairly simple thing, but it's like it's just
process
in a high
and
high pressure context.
Yeah, you just never know what you're gonna see until the interview day,
right.
And then. But the thing is you just gotta practice enough so that if you do see it, you can kind of like step by step with the interviewer work through the problems. And then that's why I've seen a lot of interviews I had done with other companies. Is that problems at first I wouldn't understand like how to solve it,
right? But
like with a bit of like help, pushing a little nudge here and there, you can work through the problems,
right?
No matter how difficult they are.
Right. What are your thoughts on the balance between getting help from the interviewer and sticking things out on your own? Because obviously like if you get too much help, it's going to like be a bad sign against you, but at the same time it is important to collaborate and work with your interviewer. Like what are your thoughts on that and balancing that? I
personally don't think there's thing as too much help, because at the end of the day the interviewer is only going to give you so much information. Right. I think your goal would,
that's a good perspective.
Yeah, your goal would to be to let the interviewer talk as much as he or she can, and just like let them freely give out the information without like you asking for it. So definitely talking out your thought process as you go along. What I like to do is the pseudocode at the start. That kind of like acts like it is a way to align myself and the interviewer on the same implementation, like how I'm going to solve this issue, so that if I do be having some issues with actually implementing it, the interviewer knows what step I'm implementing, and like if he or she can help me out on that, he or she will just blurt out a little bit. But if you're stuck, feel free to ask some help. I think I might have asked you if this is like, I try to like hint at if I'm on the right path or not. So I'll be like, do you think we can do better, or like, is it okay if I start with this? And usually if you're not quite on the money with the algorithm, the interviewer would be like, I think we can do better, and they'll like say like, maybe you're not quite there yet. So just like cluing in to if you're there or not.
And do you start with the brute force, or what is your approach? Do you I like it. Okay, pseudocoding everything out, and it's like you might be able to get to a better solution that you can implement off the bat versus, going into the implementation time on the brute force and so on. So that makes sense.
Brute force, if I see like a solution that I know is better than brute force, I will still mention the brute force, because it's always good to like tell the interviewer like, hey, I'm aware of this as a possibility, even though if I don't want to implement it, like, that's not the best solution, I'm still putting it out there for the interviewer to know that I know it at least. But if you're stuck, absolutely stuck, brute force always a good option to even just start implementing the brute force. Just there's easy ways to optimize from that as an iterative process.
All right, so thank you so much for watching. That was the interview. If you want to see this problem, you can practice this on interviewpen.com. And you can practice a lot more data structures, algorithms, system design problems. We publish 2 to 4 videos a week, continuously publishing new lessons. So if you want to practice more, go to interviewpen.com. And we want to thank Richard for taking his time to do this with us. Thank you for watching.
Of course. Thank you for having me.